how can I compete with that?
Okay, so welcome everybody on this third day of CART. I would like to introduce our first speaker of today, Linda. Linda Lesniak is a professor from Western Michigan University of United States, and she is an author of over 100 publications and the famous graph theory book, Graphs and Digraphs. And Linda, we met Linda this year when she came to Poland to participate the conference in Gdańsk, but also to find some unknown members of the family, which she found in Poland. It was very exciting for her and for us also. And I would like also to mention that Linda is a co-initiator of creating of WINCOM, which is Women in Combinatorics. It's a special platform to connect women working in combinatoric-like topics. We are very happy, Linda, that you accepted our invitation. And now we want to invite for the talk of Linda. Thanks.
Okay, do I do something now or do you do something? How do I, wait a second. Why didn't it just open up? How do I close the screen, Magda?
To share the screen like you tried before.
Oh, yeah, okay. Yeah, but now I'm doing it all over again. All right, there we go.
Okay, I think now it's okay.
Is that okay? All right, great.
Yes, it's okay.
Okay, thank you. Thank you all for inviting me. As Magda said, we met this past September in Poland. I've clearly, from my name Lesniak, I've got some Polish blood in me. Actually, I'm 50% Polish. And although I've been to Poland many times, this year was very special because I actually met my dad's two first cousins that no one from the States has ever met. So that was an incredible experience. So that's the Poland part. And next week I'm going to Mexico. So this is absolutely perfect for me to be here between those two trips. The talk I prepared today is a little bit different than most talks I've given because I was told there were going to be quite a few graduate students here. And I decided to kind of take the point of view that, you know, when you're a student, your professors help you think up problems. They give you a problem to look at, and then you go home and try to prove it or disprove it or whatever. But when you're out on your own, finally, you need to somehow come up with conjectures. How do you take old theorems and try to work with them or try to find unsolved problems on your own? And I've had a lot of students say when they get out there, this is an issue for them. So this talk is more aimed at looking at one sort of class of problems and improving existing conditions. And at the end, there will be some new research that in fact, this paper just got published this weekend that I'm going to end with. Okay, oh dear, good grief. No, this isn't moving. Let me try this again. What do I do? My slides are not moving. This was working this morning. What should I do? I'm having trouble with my slides. They won't move. So let me try that again. I mean, they worked this morning.
Try again, please.
All right, I'll try here. No, still doesn't. It's not working. I'm trying both with a. Does anyone have any ideas here?
Just double click on the slide.
Huh? Well, low tech, but we'll do that. Okay. So just in case not everyone here is a graph theorist, I'm going to be talking about undirected graphs, which means we have a collection of vertices, which I've denoted by V of G, n will always be the number of vertices, and then a set of edges. And the vertices are really just objects that may be related in some way, and that's what an edge indicates. So it might be two cities that have a direct flight between them, or two people that like each other, or any sort of situation where you have objects in some relationship, not directed in this case. Okay, so there are two very well-known problems that I want to just reference. I'm going into the class of problems where you're trying to traverse a graph with some sort of parameters given to you. You want to start someplace, you want to end someplace, and there's rules you're supposed to follow. One of these problems, and these both are very old, one of these problems is due to Euler. And in the case of the Euler situation, you want to visit every edge exactly once. You can start and end at the same place or start and stop at different places. They're essentially equivalent, but let's just always start and end at the same place. So for example, this graph, I can go through the graph and I hit every edge exactly once. So that graph would be called Eulerian. This particular problem is well studied and well answered. It has an easy characterization. It turns out that a graph, you can say yes to this if and only if the graph is connected. In other words, it's not in two pieces. I mean, you couldn't get from one piece to another and do what we are talking about without isolated vertices. And also notice that every vertex has an even number of edges coming out of it. Well, that's because as you're walking through it, you go in and you go out. So you always go through two edges every time you visit. So that makes that necessary. And it turns out it's also sufficient. And because we have such an easy characterization, there are all sorts of efficient algorithms. So this problem is well solved. But now I want to look at another problem that most of you have probably seen if you've taken a combinatorics class. Now I want to go through the graph and visit each vertex exactly once instead of each edge. Sounds very similar. For example, in this graph, I could start here and I just go around the outside and I've completed the Hamiltonian cycle. Even though these two problems sound very much alike, the second one is what's called NP complete. Now, I don't want to try to give you a formal definition of that, but first of all, it means right now we don't know an efficient algorithm to solve it. We don't know a nice characterization that can help us find an algorithm. The only algorithms that people know are essentially try all possible cases, which are exponentially bad, take so many steps. And this complete part makes it even worse. It means that if you could ever solve the Hamilton problem, you'd be able to transfer your algorithm to solve many, many other very hard problems efficiently. So if you want to be famous, you could solve this problem. Whoa, now it's working. So let's look at the problem I want to look at. A graph is called Hamiltonian. If it's possible to begin at some vertex, visit every other vertex exactly once, and then end up where you started. So we've already seen this graph, and we've seen it's Hamiltonian. And as I said, the decision problem given a graph is it Hamiltonian, is NP complete. And even worse is the problem that often arises is not only do you want to travel through the graph, but you have some sort of weight or cost on each edge. And now you want to travel through hitting every vertex exactly once and minimize the total sum. And these occur in just gobs of applications and any kind of traversal problem, scheduling problem. So I saw Bill Cook give a talk one time. It was just on these kind of problems. I'm talking about buried in your computer, buried in all kinds of algorithms are Hamiltonian questions. So what do you do? I mean, if you are interested in this problem and you hear that it's NP complete, which probably should discourage you from trying to find an efficient algorithm, well, one direction is find sufficient conditions for a graph to be Hamiltonian. Not necessarily that it's necessary and sufficient, but some property P that would be easy to evaluate that you could say, bingo, G is Hamiltonian. You couldn't necessarily say it's not. That's not what a sufficient condition does. And these kind of properties that we're going to look for generally involve, or many of them, involve the degrees of the vertices. The degree is just how many edges come in to a vertex. So like this has degree 3, this has degree 2. It's pretty clear if you put all the edges in, it's going to be Hamiltonian. So if every vertex is adjacent to everything else, that would give you a sufficient condition, but a pretty lousy one because we'll see you don't need to require all the edges in the graph. But this is going to be, we're going to be looking at degrees of vertices and how you can give properties on the degrees that guarantee you get a Hamiltonian graph. Okay, the grandfather of these kind of conditions is due to Dirac. Yeah, it's really old, from 1952. And this is what's called a minimum degree condition. We say if every vertex has some degree, and if I didn't say it already, n is always the number of vertices. So if every vertex is adjacent to at least half of the vertices on the graph, then it's Hamiltonian. Now, I'm not going to prove this. It's in every single graph theory book. But I want to show you 3 examples, and each example I picked for some particular reason. The first example, I want to apply this sufficient condition. So here we have K44. That means we have 4 vertices in one set, 4 vertices in the other, and all the edges in between. And what's the degree of every vertex here? It's exactly 4, which is n over 2. So we could apply Dirac's theorem, and we know in advance this graph's going to be Hamiltonian. Pretty easy to find a Hamiltonian circuit anyway, you just zigzag up and down. Okay, so that's my example just to show how you apply this sufficient condition. This is an example to show that it's not necessary. That is, not every Hamiltonian graph has this great big degree. In fact, this is called C6, and that's clearly Hamiltonian, and every vertex has degree 2, not half the order of the graph. And in fact, you could make an enormous cycle with 1 million vertices in it. It would still be Hamiltonian, and every vertex would have degree 2, but n over 2 would be 500,000 or something. So you can be very, 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 very far from this and still be Hamiltonian. So it's not necessary and sufficient. What's this example? Well, when you start proving theorems and you go to your advisor and you say, I've got this theorem for you, she should say, could you make it better? For example, she might say, well, will n over 3 work? So you better have an example to show nothing smaller than this works, or you don't have what's called a best possible solution for this minimum degree condition. Well, luckily, this example shows us best possible. If you look just at this graph, it's pretty clearly not Hamiltonian because it's, again, one of these bipartite graphs where you have to go up and down to build a cycle. And when you have more vertices in one set than the other, you can't complete it. So this is not Hamiltonian. And what is the degree of the vertices here? What are the degrees? Well, these are all 4 and these are all 3. So they're all greater than or equal to n minus 1 over 2. So just a little bit step down from here and you get non-Hamiltonian graphs. So in the world of minimum degree conditions, this is the best you can do. Okay, this is best possible minimum degree. So you say, well, am I stuck? No, we look at some other kind of condition. So Dirac's condition, like I said, is very restrictive. It misses lots and lots of Hamiltonian graphs. So how do you try to move forward? You want to move forward and not lose the ones you already know, but you want to get some more. That is, I want to get a sufficient condition that doesn't lose anything that Dirac did, but also get some more vertices and some graphs that have small degree vertices. So for the next couple of minutes, small means less than n over 2. Okay, that's what I mean by small. Because, for example, if I told you I have a graph, you get this big chunk that's all complete, and you put one vertex of degree 2 on, that is clearly Hamiltonian, but it doesn't satisfy Dirac. Okay, we have one vertex of small degree. Well, can we come up with a theorem that allows some number of vertices of small degree and still says Hamiltonian? And that's what Poja did. So now we've moved up 10 years. He said if you have a graph of order n, and you look at I, this I, think of it as the degree of small degree vertices. So it's less than Dirac's n over 2. For every one of those i's, if the number of vertices of degree at most I, less than or equal to I, is less than I, then G is Hamiltonian. And we'll look at an example, but so what it's doing is allowing some vertices of small degree and still getting Hamiltonian, but not too many. That's what this less than I means. So for example, the number of vertices of degree 1 is less than 1 is 0. We can't have any vertices of degree 1 in a Hamiltonian graph. Number of degree less than, excuse me, at most 2 is less than 2, that's 1, and so forth. So let's look at an example. Okay, here's a graph that has 11 vertices, and I've written the degrees down. And I want to show you that by Poiseuille's theorem, we know it's Hamiltonian. It doesn't satisfy Dirac because we have some of these little degrees here. Okay, so I've written down the degrees. There are 2, 3, 4, 5, 6, and then they're big down here. So what do we have to show? I want to show it satisfies Poiseuille. So for I equal 1, the number of vertices of degree less than or equal to 1 has to be 0. Bingo. For I equal 2, the number of vertices of degree less than or equal to 2 has to be less than 2 or 1. That's what we have. Number of vertices of degree less than or equal to 3 is 2. Number of vertices of degree less than or equal to 4 is 3, and so forth. So Poiseuille allows some vertices of small degree. Now, I think this is roughly how Poiseuille stated his theorem, but I'd like to write it another way that matches a theorem of Chvátal that we want to look at. I claim this is exactly the same as this up here. This one says you start with a graph of order n, you put the degrees in non-decreasing order. And then if for each one of these small i's, the i's less than or equal to n minus 1 over 2, it turns out that d sub I, the ith smallest degree, is at least I plus 1, then G is Hamiltonian. So D1 is greater than or equal to 2, D3, or excuse me, D2 is greater than or equal to 3, D3 is greater than or equal to 4, and so forth. And if you think about it for a minute, these two things are saying the same. So another way of thinking of Poiseuille's is if you just take the degrees and you make sure when you go to the ith position for the small i's, that number has to be greater than or equal to I plus 1. And remember, they're in increasing order, so the only small degrees have to be smaller than them. That's why they're equivalent. Okay. So we've already seen a result from the 50s, a result from the 60s. All of these results that kind of improved Dirac allowed more and more vertices of small degree. That is, the vertices of degree less than n over 2. And in a really strong sense, Chvátal hit the best. In fact, nobody's really gone beyond what his theorem is as a straight degree condition. Pardon me?
It's going to be illustrating everything that I've got now. So.
I'm sorry. What? I'm sorry, I can't understand you. Oh, well, I'm going to go on. So here is the result of Chvátal. He said if the degrees of the vertices are in non-decreasing order, and now remember Poiseuille said you had to have d sub I greater than or equal to I plus 1 for every I. Chvátal said, well, if you do have some where d sub I is less than or equal to I, but whenever that happens, d sub n minus I is greater than or equal to n minus I, then G is Hamiltonian. So if you have too many small degree vertices, but you have enough larger degree vertices to balance it out, you still get Hamiltonian. And notice that Poiseuille is a corollary of this because this never happens with Poiseuille's theorem. The d sub i's are always required to be greater than or equal to I plus 1. So vacuously, Poiseuille is a corollary. And here's an example of a degree sequence that fails Poiseuille when I is 2, but it satisfies Chvátal. Here we have I equal 2, and remember d sub I, this is supposed to be greater than or equal to I plus 1, and it's not. So this would fail Poiseuille, but the corresponding big term is large enough. D sub n minus I, d sub n minus 2 has to be greater than or equal to n minus 2, which is 9. So, and you could check all the other i's, but this example shows that Chvátal is stronger covers everything that Posia does plus more. And in another sense, remember, each time we have a theorem, we have to figure out what does best possible mean. Chvátal showed the following best possible sort of definition. First of all, suppose we have two sequences of numbers in non-decreasing order. We'll say that this sequence majorizes this sequence if term by term the q's are at least as big as the p's. Okay, so all the q's are at least as big as the p's. And what Chvátal showed was that if you have a graph with a degree sequence that fails his condition, then that degree sequence is majorized in that greater than or equal to sense, term by term, by the degree sequence of some non-Hamiltonian graph. Now you got to think about that for a minute, but it means if you tried to bring down the numbers in Chvátal's theorem there's some non-Hamiltonian graph that's bigger, greater than or equal to term by term. And so in that sense, you couldn't bring down the numbers in Chvátal's condition. And unlike other conditions for Hamiltonicity, this majorizing thing doesn't happen there. So this was the first one where we had this kind of thing happening. If your degree sequence fails Chvátal, there's some non-Hamiltonian graph whose degree sequence is term by term greater than or equal to the first one. Okay, so those are the old results I want you to keep in your pocket. And I want to shift just terminology for a moment. We'll say that a graphical sequence, now I have to make sure you pay attention to this because we're going to assume we start with a sequence that we know has a graph with that degree sequence. And it's really not cheating because there's lots of algorithms to test if a sequence is graphical. So we're going to assume always that we have a sequence that's graphical, and we'll say it's forcibly Hamiltonian if every graph with that degree sequence is Hamiltonian. Having two graphs with the same degree sequence doesn't really tell you very much. So you might have one, like say a big cycle, that degree sequence is 2, 2, 2, 2, 2, 2, 2, that's Hamiltonian. But if instead you had two little cycles, that whole graph would have the same degree sequence, but wouldn't be Hamiltonian. So we want to look at the degree sequences that force Hamiltonicity. So, and this is really just another way of saying what I've been talking about. Like, for example, Dirac says this degree sequence is forcibly Hamiltonian as long as you pay attention a little bit to parity to make sure it's graphical, because every entry is greater than or equal to n over 2. So by Dirac's theorem, this is a forcibly Hamiltonian sequence. And this is really kind of the structure of the bigger project that I've worked with for a couple of years now with Doug Bauer and Ed Schmeichel. So we just saw that Chvátal's condition for a graphical sequence to be forcibly Hamiltonian is best possible in a really strong sense, this majorization sense. Now here comes the interesting part, though. Not every forcibly Hamiltonian sequence satisfies Chvátal's condition. It's not necessary and sufficient, even though I did my best to try to convince you how strong it was. So I want to show you some examples of forcibly Hamiltonian sequences that don't satisfy Chvátal. Okay, so what does it mean to not satisfy his condition? Well, for some small I, again, I always means less than n over 2, both d sub I is less than or equal to I, and d sub n minus I is less than or equal to n minus 1, n minus I minus 1. Because Chvátal says when this happens, this has to be greater than or equal to n minus I. So we're starting with I want to show you that there exist forcibly Hamiltonian sequences where this happens for some I. In other words, they don't satisfy Chvátal. And really we're sort of aiming at, or that's what we were looking at, are there a lot of these, even though this is supposed to be such a strong condition? Well, Chvátal's advisor, Nash-Williams, came up with some examples of these things. For example, if you have n minus 1 over 2, every entry in your sequence, you can show that's graphical, and you can show it's forcibly Hamiltonian. Every graph that has this regular degree sequence, n minus 1 over 2, n minus 1 over 2, and so forth, even though it doesn't satisfy Dirac or any of these other conditions, it does force Hamiltonicity. And it's the regularity that gives you that. Okay, but it doesn't satisfy Chvátal. Why? Well, if I is n minus 1 over 2, then d sub I equals n minus 1 over 2. Everything equals n minus 1 over 2. So we have this happening. But if you do your arithmetic, d sub n minus I, which would be d sub n plus 1 over 2, is exactly n minus I minus 1. So we have one forcibly Hamiltonian sequence that doesn't satisfy Chvátal. Good start. But we'd like to find infinitely many if possible, or show that none such things exist. There's my question. How many sequences are there like this that are forcibly Hamiltonian? Every graph with that sequence is Hamiltonian, but they do not satisfy Chvátal, because most people sort of accept that you're not going to be able to do something like Chvátal did and move to a better condition. Well, actually, Nash-Williams did give an infinite family. Again, this was the supervisor. Funny story. Someone told me about this result when I was looking at this stuff, and nobody could tell me where it existed. And I found it, Nash-Williams himself would reference this result, but I never could find a proof. I even asked Chvátal, I asked Bondi, I asked a whole pile of people who told me they knew exactly where the preprint existed in their office in 1974 or something. And it doesn't appear the proof ever appeared anywhere. But I did find some proofs. And here's what Nash-Williams did. He's gonna try to move away from a regular sequence that's forcibly Hamiltonian to 2 degrees, and then use that kind of biregularity to force Hamiltonicity. And remember, we want to also fail Chvátal. So if you pick an I in the range we're always working in, and you make all the first I terms equal to I, okay, so if it's 2, you've got 2, 2, 2, 2, 2, 2, 2. And then all the rest equal to n minus I minus 1. So that's called a biregular sequence. And here's an example. And by the way, he proved that these things don't satisfy Chvátal and that they force Hamiltonicity. So let's look. Let's take n equal to 10 and I equal to 4. So if you believe this theorem says we have to have, if we have all the first 4 entries equal to 4, so up for D1, D2, D3, all the way up to D4 has to equal 4. Now this doesn't have to be I plus 1, it's n minus I minus 1. Maybe I picked a bad example, but then you make the rest n minus I minus 1, so the rest are 5s. Then you have, he proved this is forcibly Hamiltonian. That's not obvious. It's non-trivial to do that. But you have d sub 4 equal to 4, and d sub n minus 4, so that'd be 6, equal to n minus I minus 1. So this fails Chvátal for I equal 4, but he proved that it was forcibly Hamiltonian. Okay, so here's an infinite family. For each n, you've got I of these guys, I up from 1 to n minus 1 over 2, that are forcibly Hamiltonian, but fail Chvátal. So the rest of this talk is really looking at, we were looking to see if we could find a number, either lower bound, upper bound, just find out how many of these kind of sequences are there. So how might we generalize this? Okay, so we want a sequence that fails Chvátal and is forcibly Hamiltonian. And we want to sort of look at this as our role model. At least that's how I thought of it. And let's fix our I, because let's fix our I where it's going to fail Chvátal. So in this example, I was 4. And we know that this has to be less than or equal to 4. So we chose to leave this part the same. We also know that d sub n minus I, or excuse me, d sub n minus I, d sub 6 has to be less than or equal to n minus I minus 1. So that had to be 5. And of course, you know, we're kind of caught in the middle here. But what about all these out here? Could we monkey with those? So we've made sure we are failing Chvátal. We want to do something out here to make forcibly Hamiltonian. So that's the goal, right? So this is how we started, because you have to start someplace. So we're going to fail Chvátal at an I, make sure the sequence up to there is okay, and then go on. And here is what we were able to prove. Okay, I'm leaving Nash-Williams up here just for comparison. So remember, Nash-Williams says you have all of the d's equal to I for the first I terms, and then all of the d's equal to n minus I minus 1 for the rest, and it fails at I. And we're going to do exactly what I just described. That is, we're going to make the first I terms equal to I. We had to go out one more than sort of required. Remember, we're really looking at, in the theorem, we talk about n minus I. But excuse me, I've got a package that just came. I got to really stop it. I'm so sorry. My husband's gone and that thing. All right. So anyways, this is right in the middle of the big finale. So let me start the big finale again. We're going to let the first I terms be I. And then the next, we know to fail Chvátal, we have to go out to n minus I. In order to get our proof, we had to go one more. We made all of those n minus I minus 1. And then you can do anything you want with the rest. I mean, as long as you keep it graphical, unless the first I are I, all of the rest are n minus I minus 1, except the last one. And why not this? Well, I'll describe an example that shows a non-Hamiltonian graph with that degree sequence. Okay, so let's look at an example. All right, here's our theorem. So the first I equal I. We go out to d sub n minus I. We had to go at least that far, and for our proof to work, we had to go one more and be n minus I minus 1. This is the piece that makes Chvátal fail. And then what did we have to do? Well, then we had to show that any graph that had any such kind of degree sequence was Hamiltonian. This was a non-trivial proof, believe me. But here's an example. We take n equal to 10, I equal to 4. So what do? We take the first 4 have to be 4. That's just like Nash-Williams. And then out to n minus I. Now with Nash-Williams, he just went to n minus I, but we went to n minus I plus 1. So that would be 10 minus 4 is 6 plus 1 is 7. So then we go out, the next few are n minus I. That's n minus I minus 1, excuse me. That's these 5s. And then we are free to do out here as long as we keep it graphical. Okay, so if you have a graph with this sequence and it's graphical, you have a sequence, this sequence, and you show that it's graphical, which there's lots of theorems to do that, you know automatically it's Hamiltonian. That's what we proved. Anything that satisfies this is going to force Hamiltonicity. So we have a lot of flexibility out at the tail end. The Nash-Williams didn't. So we don't have all the degrees the same. We don't have just 2 degrees. You can have lots and lots of degrees out here. And it doesn't satisfy Chvátal's condition, and it doesn't satisfy Nash-Williams. So we're getting new forcibly Hamiltonian sequences. Just a quick, I don't want to run too late, but just a quick another example. If you apply this theorem with I equal n minus 1 over 2, it basically says we can do this n minus 1 over 2 out to this far, which remember Nash-Williams said if you had all n minus 1s over 2, it was forcibly Hamiltonian. But now we only have to go this far, and then you can put in anything you want as long as it, and this is interesting, buy anything here. I don't even have to put the requirement of graphical, as long as these numbers are in non-decreasing order. They're not this exception. And the only thing we have to require, we don't have to say graphical, because if the sum is even, which it has to be in a graphical sequence, then something called the Egger-Galai theorem says no matter what you put in here, it's going to be graphical. And then consequently forcibly Hamiltonian. Okay, I'm almost done. Oh, I guess let me tell you the example that doesn't work, the one that we had to rule out. Back up. I should have had a picture. I'm sorry I didn't. So this is this exception. Let me just, I'm going to have to just wave my hands and tell you what graph we have to rule out here. So fix your eye. Now think of taking a complete graph with I vertices, all the edges. So every vertex in there has degree I minus 1. I want to make these over here. Right now they're short 1, okay? And then take all but one of the rest of the vertices, make that complete. That's going to be n minus I minus 1 vertices. So the degrees will be n minus 1, excuse me, n minus I minus 2. So those are all short by 1. And then I'm going to take the final vertex and make it adjacent to everything. Now I claim that this is exactly its degree sequence. A bunch of i's, a bunch of n minus I minus 1s, and an n minus 1 up on top. Why is that not Hamiltonian? So it is this degree sequence, but it's not Hamiltonian because this top vertex is a cut vertex, if you know what that means. And a cut vertex in a graph means it's not Hamiltonian. So we actually showed that every such sequence like this is forcibly Hamiltonian, except this one. All righty. So what's the conclusion? So we've built a lot of these graphs that are forcibly, or excuse me, sequences that are forcibly Hamiltonian, but don't satisfy Chvátal. And we'll call such a thing a Nash-Williams sequence because Nash-Williams was the one who started this kind of investigation. And then we showed something that really surprised us, I think. So now think of any I that's less than or equal to n minus 1 over 2. And we could build for each one of those i's this many sequences that satisfied our condition, were graphical, and failed Chvátal. So we had a lot of work to do. You know, we have this theorem to apply, but remember, we always have to start with a graphical sequence. So just because we have an I, we have to show that for the I, for the n, there are graphical sequences that fail Chvátal, but satisfy our condition. And we found this many of them for each I. So how many did we get altogether? How many of these sequences that are forcibly Hamiltonian, but not Chvátal? Well, add them up, replace the sum by the smallest term always. That's just binomial coefficient stuff. And then by using something called Stirling's approximation formula for binomial coefficients, or excuse me, for these terms, we get this answer. Now, what does that mean? Well, first of all, n, remember, is the length of the sequence. So we have 2 to the n over root n. Whoa, that's a lot. It's an exponential number. And this big omega means there's some constant, like 14, it has nothing to do with n, such that the number of these sequences, and these sequences are the ones that are forcibly Hamiltonian, but not Chvátal, is that constant 14 times 2 to the n over root n. So there's an enormous number, it seems, of sequences that do not satisfy Chvátal, that are forcibly Hamiltonian. However, that's not the end of the story. I have to read another paper to see the end of the story. But the number of graphical sequences of order n is about 4 to the n. So it still means that there could be an overwhelmingly more number of Chvátal sequences, or the sequences that satisfy Chvátal, than those that don't. And we've gotten lower bounds on that number too. But for today, this is where I'd like to end. Just saying, I was trying to sort of walk through the research process. You know, how do you ask questions? How do you improve theorems that exist? How do you tackle old problems that nobody can fit? And even new problems, same kind of questions. Okay, thank you. Gracias and dziękuję.
Okay, thanks a lot, Linda, for your talk. I like a lot. It was quite easy to follow and quite didactic, except maybe this last part. And you were very enthusiastic, and it was visible that you like working with this Hamiltonian graphs.
It's sort of interesting, Magda, when I gave a similar talk, right, in Poland, and this very young guy came up afterwards and he said, "Oh, you have so much passion."
Yes, that's
If
true.
only I could be walking around, it'd be better. Thank you.
Okay, there is some, I don't know where there are some questions, but some remark that Hania Furmanczyk writes it's very nice talk, and Rita also very nice talk. I think the people like your talk.
I'm really sorry that I'm not there. I much, much, much prefer in-person talks. But I will be in Mexico City on the 19th or the 20th. And I've never been there, so I'm very excited.
You will be welcome anytime that you like to visit Mexico.
I apologize if I talk too fast. I come from a part of the States where we talk very fast. So I kept trying to slow down, but it was hard. Thank you.
Thank you. I think it was perfect. Very nice talk. Thank you.
Gurnor Singh says on YouTube, thank you for this needful and necessary lecture.
Magdas, can I talk to you for a moment afterwards? We have a few minutes. The Magdas, are both the Magdas here? I met two Magdas when I was in Gdansk. And we had a lot of fun, didn't we? So what time is it? When is the next talk? How do I?
Julian, you are the chief of this time.
There are no more comments on YouTube, and the next talk will be in 15 minutes. So see you in a few minutes. Just give me a second.